Hello. Thank you for joining us for today's Caringo Tech Tuesday webinar. This section's topic is object storage for advanced users. I'm Ryan Meek, Principal Solutions Architect at Caringo. And for today's webinar, I'll be your host. Our subject matter expert will be Eric Day. We'll be available to answer questions throughout the webinar. We'd like it to be interactive. So please do use the available forms and hit us with questions. We'll also be available at the end. And can stay, I don't know how long we can stay, we'll see. In addition, we have some resources available via attachments and links. Please check those out as we go. And if you have any questions after we're done, you can always reach us by email at info@caringo.com. So I've introduced myself. Eric, why don't you introduce yourself?
Okay, thank you, Ryan. I'm Eric Day. I am the Director of Product at Caringo. I've served in multiple roles in engineering and sales at Caringo, and I'm happy to be with you all today.
Thank you, Eric. We will get right in. So, about Caringo. We were founded in 2005 in Austin, Texas, to change the economics of data storage, really by enabling relentless data growth. Our flagship product, Swarm, decouples data from location, applications, and hardware, and it provides a future-proof foundation for access and data integrity, all this at the petabyte scale. And when we say petabyte scale, we mean it. So, double-digit petabyte clusters, adding petabytes at runtime, it's what we do. Our software-defined object storage solutions are used to preserve and provide access to rapidly scaling data sets in many industries, such as Department of Defense, Department of Justice, National Institutes of Health, Argonne National Labs, British Telecom, NEP, Rutherford Appleton Labs, the Brazilian court system, and hundreds more worldwide. So we're for real. And over the years, we have become experts. We have seen many advanced users actually implement object systems. And it kind of fed into the title for the webinar. Really, it reminded me, though, of this quote from Shunryu Suzuki: "In the beginner's mind, there are many possibilities. In the expert's mind, there are few." So let's not think too hard about what that means. It is a Zen saying after all. But I think the main thing he's trying to get across is keeping an open mind is one characteristic of an advanced user. It's something that we've noticed over the years. It's all about avoiding, one solution does everything, and it's all about striving for understanding. So connecting the dots between where you are and getting more and more advanced isn't really about getting a more expensive solution or getting it from a bigger company. It's really about understanding what you're building and understanding how the pieces fit together. So, okay, so great. We're open to new possibilities, but what are the right questions to ask? This is actually a great time to actually ask our subject matter expert, Eric Day. Eric, can you just tell us a few things about, what are the right questions to ask evaluating kind of different systems and when you're first getting started?
Yeah, so thank you, Ryan. Really, when you approach evaluating new systems, whether they be storage or anything else, you can come to it with either no understanding at all, or you can come to it with a lot of understanding, or somewhere in the middle. But the market is constantly evolving, and so it is important to keep educated and keep up with the changes. And the only way you can do that is by asking the questions. So I had a previous webinar where I talked about what your S3 storage vendor is not telling you. Well, if you just come to it and say, well, you do S3 storage, someone else does S3 storage, brand X, brand Y, they both do S3 storage, they must be the same. But that's not the case. And so really understanding what you need to ask about that, what are the devil in the details there, can really set yourself up for success or set yourself up for having to change course and rip it out and replace it with something different in 12 or 18 months. So one of the first things that people tend to ask about a storage system, and it's a fundamental question as well as a naive question, and that is, how fast are you? How fast does it go? And that's, as I said, that is a fundamental question because, sure, you can learn something about the speed, but it's also kind of naive in that it's usually a question that folks will ask when they don't understand, and they'll leave thinking that they've heard everything they need to know about the storage system after hearing the answer to that question. And it's really not the only important question to ask when evaluating storage. So, for example, let me tell you why. And we've seen examples of storage systems that have very, very high numbers of claimed throughput in papers that they published. But one of the things that are not discussed, for example, is how long can they sustain that for? We see some designs where people, for example, use NVMe caching or SSDs, a small amount of that, because that's very expensive stuff, in front of a large pool of questionably designed back-end storage. And so while their numbers may look really great over the course of 10 minutes or even 30 minutes worth of sustained throughput, if you try to keep that up over time, you're going to find that you're basically going to exhaust a cache there, and you're going to then experience the actual design limits of the storage system. And so we kind of have a feeling that it's called here bursty landing zones. So really, when you have a storage system that's designed with a very small amount of very fast front-end caching layer in NVMe SSDs, in hopes that you don't exhaust it before they're able to flush to the back end, that really hides a bunch of poor design that you may get to experience if you don't scale it up properly, or if your workload happens to blow right past that caching.
So would you say the correct way to phrase it would be, so how long can you sustain that ingest rate if you hear an impressive number?
Yeah, that would be how long you could sustain that ingest rate for, and also ask questions about is there a caching layer in your system? If so, how does it manage moving data between that layer and a slower backend layer, or does it scale itself up automatically? How do I grow it to make sure that I continue to get performance with it?
So growing a cluster and getting performance at the same time is a good transition to architecture.
Let me bring you back.
What do you think the follow-up question would be there?
Brian, let me have you switch back. So the one last point I want to make is that I've also seen some, I'll call them comical performance reports by folks where they claim very high numbers, and I trust that they got those numbers, but you then read some of the details about the test environment, and they deployed it on extremely exotic hardware, all SSDs, huge interconnectivity between the sites. They just sort of blew out all the numbers. And so the other question to ask is, if they published a performance paper, and by the way, we've published a performance paper too, if they publish a performance paper, ask the question, was that on hardware that you put together just for the test, or was that on hardware that a real customer of yours bought and deployed in production and scaled it up?
And quick plug, our performance white paper on customer hardware is available on your attachments and links section. Go ahead, Eric.
Yeah, and so not so subtly, I'll point out that that wasn't our hardware. That was hardware that our customer bought of their own free will, and they've scaled it up in production. And so that was a real-world performance test, not something that was on exotic hardware that no one could possibly afford to run for real.
Right. Very
okay,
important.
Okay. So also then knowing your architecture here is we see this a lot in the field is that the ring-based architecture or ring-based clustering is a common choice among some of the object vendors. And the reasoning for that is it's, from a computer science point of view, it's an easy clustering mechanism to implement. You basically come up with some sort of hashing algorithm and you sort of assign addresses within a ring of hardware. And you use that as your mechanism of distributing load and distributing storage around the system. And while that's easy to implement, it has some nasty drawbacks to it. For example, it assumes that all nodes are equal. If you just kind of take the real baseline implementation, it assumes all nodes are equal. Well, that's not the case, because 2 years from now, you're going to add different hardware into your storage cluster. You're going to add different sized drives. Maybe you're going to add servers that have more disks in them, more storage. And so now you get into the complexity of saying, well, I need to somehow express that certain nodes are able to handle more, or other nodes are able to handle less. Some are faster than others, some aren't. So now you get into this really complicated calculus of a human administrator having to figure out how to lord over and manage this ring architecture that was simple to implement, but isn't necessarily so simple to maintain and use as an end user. And so what you'd rather have is a set of nodes that really it's mesh architecture where they're all talking to each other. And a client is burdened with that, and even a storage vendor is not burdened with that task of trying to figure out who's better able to handle my request right now in the cluster, and did I add more hardware that has a different operating characteristic, more performant, less performant than the others. So you want an architecture that's going to auto-adjust itself, in real time with the dynamic changing environment of the cluster.
So Eric, are you saying that in a mesh system, the content that's already in the cluster won't rebalance?
So that's another sort of gotcha with a ring-based architecture where you're trusting the hashing algorithm to assign an address for content to live at. And what I mean by that is that if you've got X number of mailboxes and you're going to stick a balanced set of letters into each one, and you just sort of randomly choose a mailbox each time you're going to stick a letter in one, you'll achieve a balance in the system. The trouble comes when you add a new mailbox. With a mesh-based architecture, a new place to store things, a mesh-based architecture that uses a dynamic bidding algorithm will sort of migrate some old stuff over to the new place, the new node over time. It will also dynamically tend to send new requests, new writes to the new node as it once it becomes available. In a ring-based architecture, what you have is you now have a bunch of content that exists. You've changed the dimensions of the ring. That's a real fundamental challenge with the ring, is that it assumes that you're not going to change its dimensions because it achieves a balance under a stable state. And so if you change the dimensions of the ring, and by the way, I thought this was scale-out storage, so you should always be changing the dimensions of the storage cluster, the ring, you're going to have content that is now arbitrarily out of place simply because it no longer matches the address that would be assigned now as of when it was assigned previously. And so you have this rebalancing that has to take place for arbitrary reasons. in ring-based architectures. Whereas if you've got a set of cooperating nodes that are employing a dynamic bidding algorithm, then you have a cluster that can adapt to changes, but do it in a way that doesn't needlessly move content from one location to another.
Yeah, it sounds ideal to be able to incorporate new hardware, but not imply a reshuffle of content that that relies on being in some certain location.
That's right. And another thing that kind of another challenge that you tend to run into with ring-based architectures is that they kind of work on the premise that if you're going to use whole object replication, or if you're going to use erasure coding, that whatever you choose is forever locked into the DNA of that one ring configuration. So it does not play well if you want to have content that has mixed data protection schemes in it. So mixtures of different replication factors or mixtures of different erasure coding factors that typically just skipped in the ring architecture because it's very hard to implement that.
That's interesting. So you're running at petabyte scale. You are at the point where you have an architecture and you can reliably add content or add hardware by the petabyte. And you are thinking about then how to build your scale-up services. Can you sort of say a few things about the pitfalls of building those services? I mean, we have a system now that can scale. You have a backend that can scale. What are some of the fundamentals of building services along in those systems?
Yeah, so let me state that a different way, is that your architect and your storage administrator went out and they evaluated all the object storage systems out there, and they chose them because of their scaling characteristics, because of their the characteristics with low cost of maintenance, and then there's no education of the application developers in terms of how to use it right. And so you could take this really fast race car and put it in the hands of somebody who doesn't know how to drive, and they're not going to get the performance out of it that it's capable of. And so moving out of the realm of architecture choices and hardware architecture choices and hardware evaluations, you then move into, how do I use this thing effectively?
That's really interesting too, because it's not even the faster car or the more expensive hardware. You can make these mistakes with cheap hardware or expensive hardware, right? That'll debilitate an application no matter how much you spend on your infrastructure.
Yeah, actually, let me draw a parallel from, people talk about Moore's Law. That Moore's Law has been around for decades now, and we're actually starting to see a slowing of it in the CPU market. So the reasoning is because the silicon's getting to such a the features on the silicon are getting to such a small size that you can't keep doubling it. You're getting some quantum effects introducing into it now. So what we saw for a long time was that CPUs kept getting faster and faster and faster. You kept turning the clock rates up on CPUs. And that was great for application developers who had essentially single-threaded applications. Those applications kept running faster and faster, and they could get more performance out of them. And they didn't have to change the way that they fundamentally programmed. The problem, though, is that as you reach sort of the end of your performance curve with a single thing, then you start to hit the wall. And what we've seen is the need for developing parallel, threaded type applications that can take advantage of more CPUs, more cores. And so while the CPUs aren't getting faster now, look what's happening is you're taking the same speed, essentially computation pipeline, and you're starting to multiply it. So you're getting more cores and CPUs. And so think of object storage in the same way that, we're kind of constrained by our network bandwidth, interconnect between things. And so the obvious way to go faster is to multiply them, use more of them. Don't wait until you get, 100x speed improvement in your interconnect throughput, but why not just use more interconnects in parallel? And so that's really the premise of object storage, is it's not trying to be the fastest storage to write a block in a database to disk. That's going to be NVMe kind of applications. It's trying to be the most parallel storage so that as you scale it up, it fundamentally gets faster because it has more parallelism that it achieves. And so you want your application development to take advantage of that fundamental nature of object storage.
So real specifically though, how do you protect your applications from sort of shooting themselves in the foot?
And so that's it there, is that we'll talk a little bit more about parallelism in the next slide, but so how do you keep from shooting yourself in the foot with object storage, with an object storage system?
Or with any system that's just capable of going really fast and has parallel capabilities, right?
Yeah. So we've all been, as new developers, we all learn to learn to use files. fopen, fwrite, fread, close on a file. We learn to do that, and we learn to use file system directories, and that's kind of a crutch. You're bringing something. If you do that, and that's a pattern that we see a lot of times, is that people come from file system. They think in terms of folders and directories and subdirectories, and they bring that programming pattern with them to object storage. And what they find is they're bringing an abstraction that existed from a block device to better organize a block device. They're bringing that to the object storage world where that's unnecessary to do. And so in the object storage world, you should be thinking about a namespace, but not a namespace as this arbitrary set of folders or even file names necessarily, but it's really more like records. It's record identifiers within the system. So file system semantics with object storage there certainly are, and there certainly are products that put file system front ends on object storage. We have some, other vendors have them as well. But those are translation layers. If you really want the performance out of the system, you need to write natively to it. And that is, you're going to be using HTTP access methods to talk to the storage. It says on here, avoid relational databases. The idea behind that is not that relational databases are bad. They are very good at organizing related information and allowing you to query it. If that is your application, absolutely use a relational database. If you're doing storage and you're not trying to do a relational database, then by no means do not introduce a relational database into this mix if it's not necessary. Don't introduce it because that's what you know. Introduce it because that's the right choice here. So don't try to do storage in relational databases. We saw some of that. Don't try to use a relational database to keep up with things if that's not what you actually need. The other thing that you kind of pull over from the file system world is this idea of locking semantics and concurrent access to the same data. Do you really want to use locking semantics? If you need to, then do it. Absolutely do it. But don't use locking semantics if it's just a crutch to solve some parallel programming problem that you couldn't figure out. We see that a lot of times where you might do You might do a lock across all your threads because you're not sure if somebody else is going to try to do something at one time. So that can be something that's a big gotcha to your parallelism. And I put the question on here: are files locks? And we have seen applications that use files in that manner, where they will create a file in order to let other people know that I'm doing something. And so the other processes look out there and say, does that file exist as a proof of the lock? That can be fraught with hazards in a parallel environment, and especially in an object storage environment where eventual consistency is the contract. Then how fast do they become eventual consistent is more of a performance goal, but not the contract with the system.
And in that case, you're also just really relying on time to be not only the tiebreaker, but the way that different versions are distinguished from each other, right?
Yeah, so that's why the last bullet on here for benefiting from scaling is that time is important. Time synchronization or clock synchronization is important, because if you've got a parallel set of independent operators, processes running on your system, then they need to agree on what time it is. So NTP is really easy to set up. That didn't used to be the case 25 years ago. NTP was a little harder to come by, but now it's really easy to set up. It should just be done by default everywhere. Also with fundamentals, and this is not so much about object storage as it really is about what you should be doing anytime you're doing storage or other type of communication applications.
Well, this is really also, I mean, once you've decided not to use file systems, you've decided not to use databases, and these were a lot of the ways that applications would talk amongst themselves, so now you're using HTTP, presumably. How do you build resilient applications in HTTP world?
Yeah, so while the next 3 points I'm about to cover here are not specific to object storage by its nature, because it is network-based storage, will highlight any deficiencies you have in these areas. First, your application should be resilient to retries. And what I mean by that is that when you talk over a network, sometimes more often than you will when you're talking to a locally attached, direct attached disk, you'll get a communication error. It happens. We've all experienced this with our web browser, just reading web pages at night. Sometimes you need to retry to get something to get unstuck.
Mm-hmm.
A lot of us, if we were implementing on a file system, we don't think about this too much. We might error check when we do our fopen. When we first try to open the file, we might check the return value of that. But then after that, we sort of blindly read and write to the file, not expecting to ever get an error back, and never expecting to have to close the file and reopen it to try again. Because you were sort of sheltered from that when the device was local to the system you're working on and direct attached. But when you get the storage away from where your clients are operating, that becomes a very important thing to do. And so error code checking, intelligently respond to the return codes that you get back when you're doing communications. For example, if the client tells you that, I'm too busy right now, that doesn't mean keep slamming on it. Maybe you should back off and wait a bit.
Don't just sit in a retry loop.
Don't just sit in a retry loop. Send the document to the printer 10 times, because maybe it'll print on that last 10th time. So your application needs to think about, what are some graceful error handling characteristics that I can have? And I don't just mean blow an obscure error to the screen that says, call your tech support person with error 35832. That means, is there a way that your application can do the right thing for the user that is using your application right now? Can you retry without, maybe you notify them that you're trying to retry, or if it's taking extra long time, maybe you tell them a more intelligent thing than just, error code XYZ.
Well, maybe you retry to another location.
Yeah, exactly. And the other thing I meant by graceful error handling is that you do not want to leave, if you've got this as part of a pipeline, sort of a transaction set, you don't want to blow up in the middle of that. You want to gracefully unwind what you've done. So don't leave dangling database records because you failed, partway through the operation. So you need to think about that stuff.
So real specifically then, I mean, a lot of that, like you said, was sort of application design, not to inhibit scaling, right? And well-behaved applications. This is a little more specific to object storage, and actually it's pretty specific in some cases to Swarm. Can you just talk a little bit about, why parallel uploads and downloads are important, and how they and how they benefit advanced users? I mean, you've seen users do this right, and you've seen users, do it in a way that doesn't benefit, right? So,
right.
What are the important takeaways are here?
Okay. So parallel uploads first are really, think about parallel writing. If you're coming from a file system world, the first thing you're doing is going, what the heck is that, and why would you do that? Because you're thinking about, I'm writing to my local disk drive on the system. Why would I write with multiple threads to a file? Well, when you get out into the network, realm, even if you're using NFS, by the way, you will find that one socket connection is rarely able to saturate the network pipe you have between a client and its endpoint. That you need to use multiple socket connections in order to fully saturate the single pipe that a particular endpoint, client to endpoint has. So parallelism can come from using multiple sockets from the same host to the same storage location. But I also talked earlier about parallelism being, maybe you're not using just one client. Maybe you've got a file. We had an interesting customer that was doing something with they had a large distributed cluster. It was a compute cluster. And so the compute cluster actually had this virtual memory image that spanned multiple host servers. And so they wanted to periodically take snapshots of this entire virtual memory image in this compute cluster. Well, now we're not just talking about address 0 to address X of a RAM in one system. We're now talking about the actual overall address space existing across multiple hosts. And this is where parallel writing became exceedingly important, because you would not want to have one host just write all of its stuff and then go to the next host, have it write its stuff, and then the next host. You want to have all of those hosts write in parallel to the storage system. And you want to be able to have a storage system that can absorb that amount of parallelism from all those different endpoints and scale out with it. And so parallel writing can be used to increase bandwidth from a single host, but it can also be increase your bandwidth when you're talking about multiple hosts right into the operating system. So that's about speed. The other reason to use parallel uploading is that it is, in its essence, or parallel writing, is that you are in essence writing pieces of a whole thing, of a whole file, in chunks to the system. And as I said in the previous slide, be resilient to error cases. What if one of those fails? What if the socket connection has a glitch and fails for a moment there? Well, you wouldn't want to restart the entire, if you're sending a multi-terabyte, even multi-gigabyte file, you wouldn't want to restart that whole thing. You'd rather just pick up from where you left off. And that's where parallelism can come into play there, is that it allows you to say, you know what, here's the next piece, and then here's the next piece, and here's the next piece, now I'm done. And that's the point of the parallel writing in object storage. It's also very good when you do not know the length of the thing that you're going to be writing. That's very typical if, for example, this webinar right now is being streamed to a storage system somewhere. They don't know when we're going to stop talking. And so if you're doing some sort of streaming media, you're doing video capture or audio capture of some kind, or even data capture from instrumentation, you may be going along and saying, here's the next chunk of data, here's the next chunk of data, here's the next chunk of data. Oh, we're done now. Okay, we're done now. Complete that package, complete that write to the system. Anything to add?
You briefly, yeah.
Parallel reads.
Yeah, you briefly touched on it too when you said, perhaps terabyte-size files. It seems like this is partially, related to multi-part uploads, and could enable things like objects that are larger than disks, right?
Oh yeah, certainly so. In the case of that, I was talking about that large compute cluster's virtual memory image. It was quite a bit larger than any single disk drive to it. And so to effectively spread that load around a storage cluster and even to find disk drives to put it on, you had to break that up into these multi-part write operations.
Mm-hmm. So what about parallel downloads? What's
didn't want to leave those.
What's the key takeaway there?
So parallel downloads are really just what are called range reads out of the system. And you may think of range reads as, that's how I seek to a specific point in a video that I'm watching. And that is true. That is absolutely true. But that's thinking about it as a very single-threaded point of view. Because you're thinking about, well, I could just start reading at some arbitrary point in the file, or maybe the file has a structure to it where I can read the header, the directory information for it, and then jump to the spot that I need. And that's an excellent example of using range reads. Another way to use range reads, though, is kind of the opposite of what I was talking about uploading, is that you can open multiple socket connections to download multiple parts of a single file at a time in order to achieve more speed from either a single host talking to the storage system, or from multiple hosts talking to the storage system and doing some coordinated activity with themselves. It also gives you a way to do the retry. Oh, so the restartability, the restartability argument comes into there too. Is that if I was reading something and I got 50% of the way through it, and then there was a glitch in the socket, there's no reason to start over from scratch. Just continue from where you left off by doing additional range reads from that point on.
Yeah, and it's on the download side especially. You can stop thinking of consuming all of every object, or reading all of every object that you touch on the wire. You can really just start thinking about grabbing the part that matters, whether it's the beginning of the video or the slice into the satellite picture that the user in front of the application needs to see. It's a great way to be more efficient, right?
Yeah, that's right. Video streaming is probably the easiest one to talk about because most people have experience with it. If you start playing a video and you want to just jump an hour into a 2 hour long video, there's no reason to download that first hour worth of the video. Just jump to the spot you want to start playing from and go from there. But the pattern exists in more files than just video.
Absolutely. So we touched a little bit on those parallel uploads and parallel downloads. That was one of the things that got me thinking about kind of adding this content, because one of the really great ways to actually see that in action is using command line clients. A lot of, and you see that in a lot of advanced users. You see it in a lot of advanced shops. We think, you can say a little more about this, Eric, but I think, when we've talked about it before, it seems like you've settled on these as really excellent building blocks to understand what you're doing. Am I right?
Yeah. So I actually come at them from you want to become, you want to understand what it is you're doing. If you just, let me back up a second. If you were just dealing with an abstraction that an SDK has given you of, I'm going to open a file, I'm going to read from a file, I'm going to write to a file, I'm going to close it. If you have an SDK that abstracts object storage from you in that way, that's fine. That'll work. That'll work for a lot of things. But then something happens and the system can't connect. Something glitches. You don't understand it. You're thinking back to your file system of, I'm trying to open a file. What's it mean by I don't have the right authentication method, or I've got something else going wrong with it? Well, if you don't understand what the SDK is trying to do, you don't understand what the SDK is doing behind the scenes for you, then that can leave you very mystified in terms of how even to go about addressing the fix for a problem. And so command line tools, curl, say what you will about its complexity of command line options. Curl is a very good, tried and true, stood the test of time tool for understanding web page communications. You turn on the -v flag with the curl command line, you can see all of the request headers, all of the response headers that come back, and you glean a lot of information from it. And if you're out there saying, well, I've been doing web programming for years, and actually I don't know what you mean by request headers and response headers, that's what I mean by you need a deeper understanding of, what is the actual communication that's taking place back there? What does it mean to have a particular authorization header on the request? What does CORS mean? That's some ideas there. Command line clients are also really good at incrementally testing your code logic. And so when you're coding, if you say, I'm going to just write a big application, you start from the beginning and you write all the way to the end, you do everything, you just got 100 modules, and now you're going to test it. Now I'm done writing, I'm now going to test it.
Your classic waterfall.
We're now going to understand what kind of disaster that's going to be. And so you want to be able to modularize your code, make it into unit testable components. And a great way to do that unit testing, or to prove out the process that it's going to use, is by using command line client tools, curl, S3 command, AWS CLI. Those are some examples of tools that are usable. Now, command line tools are not just for testing and greater understanding. I'm a DevOps sysadmin guy. I actually use them quite a bit for actually writing real scripted applications, that do real sysadmin work behind the scenes. S3 command, I've got a lot of mileage out of that. I've done the same thing with curl, and still do to this day with it. So it's not just that command line tools are for the developer learning how to use it or test something. They can be used as a handy way to encapsulate a bunch of programming knowledge that you don't have to now re-implement if you're just trying to do some scripts to talk with your object storage system. So curl and the like are not just for talking to web pages. They are for talking to object storage systems, since they also use the HTTP protocol. And that's maybe kind of
curl comes to mind, S3 command comes to mind, what AWI client comes to mind, or AWS client comes to mind. Any others you would sort of think of off the top of your head there?
No, at that point you started to get into standard HTTP implementations that you have in the various languages.
Right.
You talk about those. You may not need that fancy. You may not need an SDK from the vendor. You may, the HTTP communications that you have in your language may be sufficient for it for a lot of things anyway.
Okay, so you have a backend that scales. You have applications that scale. You're running a modular project. You're using command line clients. Can you bring it back home for us? Talk a little bit about RTO and RPO and your requirements, because we've come this far without really getting to those specifically. And with
we have
on the clock, we're going to bring it in the next 10 minutes or so.
Ryan's talking me down from the ledge, from my soapbox anyway. So certainly storage administrators and systems architects absolutely know what RTO, RPO is. If you're a new application developer and you're saying, I'm not quite sure what those are, no one's ever asked me to worry about them, well, it's time to learn what they are, and it is time to worry about them, because as an application developer, you have an influence over them, especially with object storage. Back in the day with file systems, storage administrator deployed a file system, they set up a certain level of RAID or mirroring on the box, and they stamped it as this has a recovery point objective of last committed transaction or last 5 minutes worth of committed transactions on the disk storage system. So recovery point objective is RPO is if I had a loss right now, and you define what the loss is, you might say if my network connection dies, or if a single disk drive dies, or if an entire server dies, or if an entire data center dies. You define what the failure mode is, and you say if that happens, then I can recover. It doesn't say when you'll be able to recover, but once I do recover, I will be whole back to this point in time. Mm-hmm. And then the sort of matched rule with it is then the recovery time objective, which says if this kind of failure happens, the application or the users of this system will experience an outage for this period of time before the system becomes responsive to them again, or before data comes back online. And so what does this mean in an object storage world? And why, as an application developer, do you have some influence over this? Because in the object storage world, you're now introduced to concepts like the question of what kind of protection level do you want on this file or this object that you're writing to the system? When you're writing to a SAN or a NAS, you were never asked that question. The storage administrator set something up, and whatever you wrote, the system just protected it in the way that the storage administrator set it. Now you get to things like, do I want reduced redundancy? Or do I want standard protection in an object? Do I want, this is not quite one of these concepts, but do I have infrequent access to objects? So these kinds of things become important decisions that now an application developer is brought into the loop on. And so we have additional training on our use of multiple replication factors, as well as multiple erasure coding schemes within our system. These are all choices you get to make during development. And so the choices really come to a trade-off between footprint, so how much additional overhead are you using for data protection or for performance, because whole object replicas have a big performance impact. They can greatly improve your performance versus the footprint. So the footprint versus availability of your content becomes a choice that you get into. So in the interest of time, let's move along. Another thing that you're now exposed to is namespaces. I mentioned before that we kind of came up from a world of using file systems, and in file systems you have, as you move from the historians are going to correct me here, but like as you move from the PDP 8, the RSX systems to PDP 11 and got to the VAX-based systems, they introduced They now introduced hierarchical directory structures. And we've grown up with that concept of directories and subdirectories and so on until you get to a file. But I would propose to you that your namespace and object storage doesn't necessarily need to be human recognizable names. You might be getting randomly assigned identifiers for objects. And in spaces where the name of the object has no meaning to the application, is just purely an identifier, why are you taking a lot of time to worry about, what the name of it is or what the structure of the name is? One of the things you see right away.
We haven't said too much about it, but doesn't that imply you also have a metadata system that scales?
That does. So thank you. So really, in an object system, one of the interesting things was, let me just go back to S3. S3 has buckets and object names. There are no directories in S3. There's bucket and the name of the object. Now, people simulate the concept of directories by having an object name that has slashes in it. Those look kind of like subdirectories on the system, and there are applications that use them as such. And if you need to do that, perfect, do that. But if you really don't need to do it, then the name becomes less important. What becomes important, though, is how are you going to locate something? So if you've got an object storage system and you have billions and billions of objects in it, how do you go about searching through the contents that you have there? And that's where metadata comes into play. And we have additional presentations on the importance of metadata and how you can use a metadata as a multi-dimensional access layer to the storage within your system. Now, how many of you have you come up with a neat folder structure on your computer for storing your documents, and then you realize that some of those documents should span multiple trees within your storage system? What you're experiencing there is that files don't always naturally fall within one grand single directory hierarchy to rule them all. That a lot of times you need these multi-dimensional access to it, and that context is really important when you're doing that. And that's where metadata and metadata searching semantics becomes exceedingly important with object storage. Last thing about namespaces I want to say is that fortunately not a lot of vendors do this anymore, but some will still create these data islands or data lakes where, objects written through one protocol are not accessible through the other under the same namespace. So you really want an object system that no matter what your access protocol is to it, that you're still seeing the namespace in the same way that you see it through the other access methods.
I think that's well said, and I think that's a good place to move on.
Yep.
Let's see here. To go right through it, I mean, we reviewed data protection, we reviewed replication, erasure coding, time servers matter, automate everything, that especially related back to command line clients and modular applications. You want to say a few more words and bring us in, Eric?
Yeah, I didn't quite touch on that, but the DevOps philosophy that has really emerged over the last several years is that system administrators should, they shouldn't do anything manually more than once before they automate it. And if you automate something, what you've done is you have now codified the process in a way that other people can read it and see what is happening. So really, system administration and application development are sort of merging into DevOps in a way that now your system administration, the setup of your systems, the usage of your systems is really more like code. It can be checked into a source control system, and that's where scripting and automation or scripting plays into that automation, is that you can check in the scripts. You can check in how I set up a system, how I use my storage, what are my processes on storage. That can all be automated, and object storage really helps with that because you now have this singular namespace that's sort of globally available from anywhere you hit it from. So the fact that I'm running on I plug in a new server into my environment. I don't have to hope I can find the SAN connection for it to reach into the system, or make sure it has the right connectivity with disk drives it needs. Rather, I just know I'm talking to this HTTP-based object system that, as long as I have network access for the thing, then it has access to everything else all the old servers have been doing, and I can check the code out from that, and I can run my processes on it immediately.
And you have success.
That's right.
Hey, thanks everyone for joining us. It's been an absolute pleasure. To keep up with Caringo, follow us on Twitter or LinkedIn. If you have additional questions or would like us to schedule a custom demo, please email us at info@caringo.com. I'd also like to invite you to join us for our upcoming events. January 30th is the debut of our new Brews and Bytes webcast with discussions about technology and storage. This month is how object storage can help you in the roaring 20s. And our next Tech Tuesday webinar is on February 18th, where our topic will be best practices for object storage. Thank you, Eric, and thank you everyone for joining us today. It's been a pleasure.